Hundreds of volcanoes are erupting right now in our solar system, all on the same world. Earth feels like the volcanic powerhouse of our neighborhood. That assumption crumbles when you see what's happening on Jupiter's moon. Tonight we're discovering how gravity becomes a furnace, how sulfur becomes a major geological player, and why this moon rebuilds its entire surface faster than any world should. Before we dive into this volcanic nightmare, drop a comment about the most extreme weather you've experienced. If you enjoy these cosmic journeys, consider subscribing. These explorations of alien worlds are meant to be shared. Scientists expected O to be dead, a cold, cratered moon like ours. Voyager 1 changed everything in 1979. The spacecraft photographed Jupiter's moons during its flyby. What it found on O shocked the scientific world. Massive columns of material shooting into space. Not one, not two. 9 separate volcanic eruptions caught in the act. This was the first time humans had seen active volcanoes on another world. Navigator Linda Morabito spotted the first eruption while checking photos. A strange umbrella-shaped cloud extending beyond the moon's edge. That cloud was volcanic material blasting upward at tremendous speed. O hosts over 400 active volcanoes. That's more volcanic activity concentrated on one small world than anywhere else in our solar system. O sits too far from the sun to stay warm. By all logic, this moon should be frozen solid. Instead, it generates more heat than worlds, 10 times larger. Jupiter's gravitational pull creates something impossible on independent worlds. The giant planet squeezes O like a stress ball, continuously, for billions of years. O follows an oval-shaped path around Jupiter. This path gets stretched into an ellipse by the gravity of other moons. As O swings closer to Jupiter, the planet's gravity grows stronger. The moon's rocky interior gets stretched and squeezed. When O moves farther away, that interior relaxes. This constant flexing generates heat through friction, the same way bending a paperclip back and forth makes it hot. The energy from this process melts parts of O's interior. Without Jupiter's gravitational massage, O would cool dramatically within millions of years. As volcanoes work differently than Earth's, sulfur and sulfur dioxide shape much of the surface activity we see. Sulfur melts at much lower temperatures than rock. This creates a very different kind of volcanic landscape. Yellow liquid sulfur flows across the surface like rivers of paint. The temperature determines the color. Yellow when cool, red when hot. Sulfur dioxide erupts as powerful geysers. These gas plumes shoot hundreds of kilometers into space. When the gas cools, it falls back to the surface as sulfur snow. The entire moon gets coated in sulfur compounds. This gives O its distinctive yellow, orange, and red appearance. No other world in our solar system looks anything like it. Earth's volcanoes need temperatures over 1000 degrees Celsius, as sulfur-rich surface activity can happen at much lower temperatures. O rebuilds its entire surface faster than any other world. The volcanic activity never stops. New lava flows bury old ones within years. Massive volcanic explosions create and destroy features constantly. The surface we see today didn't exist a million years ago. In cosmic terms, that's incredibly young. This rapid change means it has no impact craters. Asteroids hit the moon regularly, just like everywhere else. But fresh volcanic material buries the craters before they can accumulate. Scientists estimate the entire surface gets replaced every million years. That makes O the youngest surface in our solar system. The constant volcanic activity creates a patchwork landscape. Smooth plains of recent lava flows, towering volcanic mountains, calderas, giant collapsed craters where underground magma chambers emptied. Jupiter surrounds itself with a powerful magnetic field. This field traps charged particles from space, creating radiation belts around the planet. O orbits directly through these radiation belts. The volcanic activity constantly adds new material to this harsh environment. Sulfur and oxygen from ice volcanoes get ionized by radiation. This means they become electrically charged particles. These particles follow Jupiter's magnetic field lines, creating a donut-shaped cloud around the entire orbit. This interaction generates electrical currents between Io and Jupiter. The current is extraordinarily powerful. The charged particles also create aurora displays in Jupiter's atmosphere. These appear as bright spots and trails near Jupiter's poles. Io has an atmosphere, but it's incredibly thin. You couldn't breathe it, and it barely registers compared to Earth's thick air. This atmosphere comes largely from volcanic activity. Sulfur dioxide gas from erupting volcanoes creates most of it. Some sulfur compounds on the surface also turn directly from solid to gas. The atmosphere changes dramatically between day and night. During Io's day, surface heating turns more sulfur into gas, thickening the atmosphere slightly. At night, the gas freezes back onto the surface. When Io passes behind Jupiter and enters the planet's shadow, the atmosphere partially collapses. Most of the gas condenses and falls as frost. This creates one of the most dynamic atmospheric systems in our solar system. The entire atmosphere essentially breathes in and out as Io orbits Jupiter. Io doesn't orbit Jupiter alone. 3 other large moons, Europa, Ganymede, and Callisto, travel around the giant planet in a complex gravitational dance. The inner 3 moons maintain a precise relationship. For every 4 times Io orbits Jupiter, Europa orbits twice and Ganymede orbits once. This mathematical relationship is called orbital resonance. This resonance keeps Io's orbit slightly elliptical instead of circular. Without Europa and Ganymede's gravitational tugging, Io's orbit would become circular. The tidal heating would stop. The volcanoes would shut down. The Moon's system acts like a finely tuned machine. Each component affects the others, as volcanic activity depends entirely on this gravitational cooperation between the moons. This resonance has remained stable for billions of years. It ensures as volcanic fury continues indefinitely. Exploring Io presents unique challenges. The radiation environment around Jupiter can destroy spacecraft electronics quickly. The volcanic activity makes landing dangerous. The lack of atmosphere means no protection from space hazards. The Galileo mission provided our best close-up views of Io during the 1990s. Even this heavily shielded spacecraft could only make brief flybys. Extended observation would have meant certain destruction. Future missions must balance scientific goals with survival needs. Proposed Io missions include heavily radiation-shielded orbiters and potentially heat-resistant landers designed to survive the volcanic environment. The scientific payoff would be enormous. Direct analysis of sulfur volcanic processes, understanding how tidal heating works in detail, insights into volcanic activity that could apply to other worlds. Io represents an extreme natural laboratory. The lessons learned there could revolutionize our understanding of planetary geology throughout the universe. What happens when 3 moons move in perfect mathematical harmony? They create one of the most powerful heating systems in our solar system. Io doesn't orbit Jupiter randomly. Neither do Europa and Ganymede. These 3 moons follow an exact mathematical pattern. For every 4 times Io completes an orbit, Europa orbits exactly twice. Ganymede orbits exactly once. This precise timing is called orbital resonance. Think of it like 3 dancers moving to the same beat, but at different speeds. The resonance amplifies gravitational effects dramatically. Each time the moons align, they pull on each other with extra force. This happens over and over in the same pattern for billions of years. Without this mathematical relationship, Io's orbit would gradually become more circular. The heating would drop. The volcanoes would fade. Why can't Io settle into a nice circular orbit around Jupiter? Europa and Ganymede won't let it. Every time Io tries to move into a circular path, the other moons interfere. Their gravitational tugging forces Io back into an elliptical orbit. This creates a cosmic tug of war that never ends. An elliptical orbit means Io's distance from Jupiter constantly changes. Sometimes closer, sometimes farther. This varying distance is crucial for the heating process. The orbit stays just eccentric enough to generate strong internal stress. Too circular, and much less heating occurs. Too elliptical, and the orbit becomes unstable. This forced ellipse has persisted for billions of years. The gravitational dance maintains the conditions needed to keep O's interior hot and partially molten. Jupiter's gravity doesn't affect his entire body equally. The side facing Jupiter feels a stronger pull than the far side. This difference creates a stretching effect called tidal force. As Io orbits closer to Jupiter, the stretching intensifies. As it moves farther away, the stretching relaxes. The rock inside Io behaves like putty under this constant flexing. Solid rock can only bend so much before it starts generating heat through internal friction. The deformation happens in cycles matching O's orbital period. Stretch, relax, stretch, relax. Each cycle generates more heat through rock friction. Over millions of years, this steady flexing produces enough energy to melt much of Io's interior. Deep inside Io lies a largely molten layer of rock. This underground ocean of liquid rock extends through much of the moon's interior. Tidal heating melts rock at temperatures exceeding 1200 degrees Celsius. At these temperatures, even the hardest minerals become liquid. The result is a vast magma ocean beneath O's thin solid crust. This molten interior constantly seeks ways to reach the surface. Pressure from below pushes the liquid rock upward through cracks and weak points in the crust. The magma ocean does not fully solidify because the tidal heating does not stop. New heat constantly replaces much of the energy lost to space. This creates a perpetual cycle. Heat melts rock, rock becomes magma, magma erupts as volcanoes. How does heat from O's deep interior reach the surface to power volcanoes? Through an incredibly efficient thermal transfer system. The molten interior creates convection currents, just like boiling water in a pot. Hot material rises toward the surface while cooler material sinks back down. These currents transport enormous amounts of thermal energy upward. The heat moves through the interior much faster than simple conduction through solid rock. Near the surface, the rising heat encounters the thin solid crust. This creates weak spots where magma can break through and erupt. The entire process works like a planetary heating system. Heat generated deep inside gets delivered directly to volcanic regions on the surface. Most rocky worlds get much of their internal heat from radioactive decay. Io breaks this rule almost completely. Radioactive elements inside planetary interiors decay slowly, releasing small amounts of heat over billions of years. This process helps power Earth's geological activity. Tidal heating on Io produces vastly more energy than radioactive decay. The gravitational flexing generates heat equivalent to many times what radioactivity could provide. This explains why small Io stays more geologically active than much larger worlds. Size doesn't matter as much when you have an external energy source this powerful. The energy difference is so extreme that Io would remain volcanically active, even with very little radioactive heating. As volcanic activity slowly changes the moon's orbit over cosmic time, each eruption represents energy that ultimately came from orbital motion. As Io loses energy through tidal heating, the moon's orbit changes over time. The process is incredibly slow. The changing orbit affects the strength of tidal heating. Farther from Jupiter means weaker tidal forces and less internal heating. However, the orbital resonance with Europa and Ganymede helps maintain the system's stability. The other moon's gravity keeps O's orbit from changing too quickly. This creates a self-regulating system that has sustained O's volcanic activity for billions of years. What keeps this complex gravitational system stable for billions of years? The answer lies in the physics of orbital resonance. The three-moon resonance creates a gravitational balance that resists disruption. Any change in one orbit tends to affect the others and restore the pattern. This stability has survived cosmic impacts, gravitational perturbations, and billions of years of orbital evolution. The system essentially locks itself into the current configuration. The resonance ensures O can continue receiving tidal heating for a very long time. Barring major cosmic catastrophes, the volcanoes may keep erupting for billions more years. This represents one of the most stable dynamical systems in our solar system. Tidal heating doesn't affect all parts of O equally. The heating varies dramatically based on location and orbital position. Areas facing Jupiter during closest approach experience maximum tidal stress. Regions on O's trailing side feel different heating patterns. This creates hot spots and cold spots across O's surface. Some volcanic regions stay continuously active while others erupt in cycles. The heating pattern also shifts as O moves through its elliptical orbit. Different areas become more or less active depending on orbital position. These regional differences explain why O's volcanic activity isn't uniformly distributed across the surface. O's unique chemistry creates volcanic activity at surprisingly low temperatures. Sulfur compounds melt at much lower temperatures than rock. The interior temperature needs to exceed only 120 degrees Celsius to melt sulfur. Compare this to the 1200 degrees needed for rock volcanism. This low melting point means tidal heating can easily maintain sulfur volcanism, even when rock remains solid. Much of O's surface activity involves sulfur rather than only true rock volcanism. The temperature difference explains O's distinctive appearance. Colorful sulfur compounds cover the surface instead of the gray rock typical of other volcanic worlds. This creates a world where volcanism operates under very different rules than on Earth and other rocky worlds in our solar system. You can't see anything like this on Earth. Rivers of bright yellow liquid flowing across an alien landscape. As volcanoes are famous for sulfur and sulfur compounds spread across the surface, some flows and hot deposits can look strikingly different from Earth's familiar volcanic scenes. This creates something that feels alien to human experience. Pure sulfur melts into a golden liquid at relatively low temperatures. When sulfur-rich material appears around active areas on O, it can flow like thick honey across the surface. The result can look like rivers of liquid paint streaming down mountainsides. These sulfur-rich flows and deposits can stretch for dozens of kilometers before cooling and solidifying. The patterns spread across O's surface and change with each new eruption. No other world in our solar system shows sulfur activity on this scale. This makes O's landscape unlike anything humans have ever witnessed. Gas eruptions on O dwarf anything Earth can produce. These aren't gentle steam vents. They're massive geysers of sulfur dioxide blasting into space. Sulfur dioxide can exist as frost, liquid, or gas depending on local conditions. When underground pressure builds up, this gas erupts with tremendous force. The eruptions create towering columns that reach hundreds of kilometers high. These gas plumes move faster than rifle bullets. They carry sulfur particles and other volcanic debris far above O's surface. Some material escapes into space entirely. The eruptions happen suddenly and violently. A quiet region can explode into activity within hours, shooting massive gas clouds into O's thin atmosphere. Earth's volcanic gas emissions look gentle compared to O's sulfur dioxide geysers. Temperature controls everything about sulfur's appearance on O. Hot sulfur looks completely different from cool sulfur. Fresh sulfur often appears bright yellow under cooler conditions. As the temperature rises, the color can shift dramatically. Hot sulfur can look orange, then red, then deep crimson. This happens because sulfur molecules change their structure at different temperatures. Cooler sulfur tends to favor ring and chain-like forms that can look yellow. Hotter sulfur shifts into forms that can look darker and redder. The color changes happen rapidly as sulfur-rich material cools on O's surface. A single hot region can display yellow, orange, and red bands showing its temperature history. This creates O's distinctive multicolored appearance that makes it instantly recognizable among solar system moons. As sulfur activity operates under very different temperature requirements than Earth's rock lava, it needs far less heat to appear and flow. Rock volcanism requires temperatures exceeding 1000 degrees Celsius. Sulfur melts and flows at only 120 degrees Celsius. This dramatic difference changes how sulfur behaves near active volcanic regions. The lower temperature requirement means even modest heating can mobilize sulfur and sulfur compounds near the surface. Mild local warming can help create visible sulfur activity on Io. This helps explain why Io shows so many colorful active regions despite its small size. The energy needed to melt sulfur is much more accessible than the energy needed to melt rock. Earth would need much more widespread high-temperature volcanism to match Io's level of visible surface activity. Solid sulfur dioxide on O's surface can disappear directly into gas without melting first. This process is called sublimation. In O's low-pressure environment, sulfur compounds can transition straight from solid crystals to gas vapor. This happens when surface materials get heated by sunlight or nearby volcanic activity. The sublimation process constantly adds sulfur vapor to Earth's thin atmosphere. This creates a steady flow of material from surface to atmosphere without requiring volcanic eruptions. Different areas of Io's surface sublime at different rates. Regions with fresh sulfur dioxide frost contribute more vapor than older, weathered areas. This process helps maintain Io's atmosphere even between major volcanic eruptions. Sulfur atoms can arrange themselves in several different molecular patterns. Each arrangement creates sulfur with different properties. Temperature and pressure determine which molecular form dominates. Cool conditions can favor rings made of 8 sulfur atoms. Hot conditions create different arrangements with varying numbers of atoms. These different molecular forms help explain sulfur's color changes on O. Each arrangement interacts with light differently, producing distinct colors. The transitions between molecular forms happen constantly as O's surface heats and cools. This creates a dynamic chemical system unlike anything on rocky worlds. Understanding these molecular changes helps scientists interpret O's colorful surface patterns. Sulfur doesn't exist alone on O. It combines with oxygen to create a variety of chemical compounds. The most important compound is sulfur dioxide. Sulfur combined with 2 oxygen atoms. This gas powers many of O's dramatic eruptions and forms much of the Moon's atmosphere. Other sulfur-oxygen compounds form under different conditions. Some appear as colorful surface deposits. Others exist only at high temperatures inside volcanic vents. These chemical reactions happen continuously across O's surface. Volcanic heat drives new compound formation while cooling allows different compounds to form. The variety of sulfur compounds gives you its complex surface chemistry that's far more diverse than simple rock-based worlds. Material blasted into space by O's volcanoes doesn't stay airborne forever. It falls back to create colorful deposits across the surface. Sulfur particles and sulfur dioxide gas cool rapidly above the surface. As they fall back down, they create layers of colorful material that coat O's landscape. Different compounds create different colors. Pure sulfur creates yellow deposits. Sulfur dioxide creates white patches. Other sulfur compounds produce orange and red areas. These deposits accumulate over time, building up complex layered surfaces. Recent eruptions create fresh, bright deposits while older material fades and darkens. The constant volcanic fallout means Eye's surface colors change continuously as new material covers old deposits. Gas eruptions from O create distinctive umbrella-shaped clouds that spread high above the surface. These structures form due to the physics of gas expansion in near vacuum. Sulfur dioxide gas blasts upward from volcanic vents at tremendous speed. As it rises higher, the gas encounters O's extremely thin atmosphere and begins to spread outward. The expanding gas creates a characteristic umbrella shape with a narrow stem and wide cap. This pattern is visible in spacecraft images as dark shadows against surface. These plume structures can persist for weeks or months. They gradually disperse as the gas either escapes to space or condenses back onto the surface. The umbrella shape helps scientists track volcanic activity and measure eruption strength from great distances. Sulfur on O moves continuously between solid, liquid, and gas phases in a complex circulation system. This creates one of the most dynamic chemical cycles in the solar system. Volcanic heat melts solid sulfur deposits into liquid flows. Continued heating can turn sulfur into gas vapor. Cool conditions reverse the process, turning gas back into liquid and then solid form. This cycle operates on multiple timescales simultaneously. Rapid changes happen during eruptions. Slower changes occur as surface materials respond to solar heating and cooling. The circulation moves sulfur compounds between Earth's interior, surface, and atmosphere. This connects all parts of the Moon into a single integrated chemical system. No other world shows such active cycling of sulfur compounds across all three phases of matter. Most rocky worlds keep their scars for billions of years. O erases its entire surface faster than any world should. Scientists measure surface age by counting impact craters. More craters mean an older surface that hasn't changed much. Fewer craters indicate recent geological activity. A surface averages less than 1 million years old. In cosmic terms, this is incredibly recent. Most planetary surfaces date back billions of years. This extreme youth means Earth's surface didn't exist when early humans first appeared on Earth. The landscape we see today formed entirely during recent geological time. The rapid surface renewal makes Earth the youngest world in our solar system. Fresh lava doesn't just add to Earth's landscape. It completely buries and replaces what came before. New volcanic eruptions spread liquid sulfur and molten rock across existing terrain. These flows fill valleys, cover hills, and erase previous surface features entirely. The burial happens remarkably quickly. Lava flows can cover hundreds of square kilometers in a single eruption event. Multiple eruptions per year mean constant landscape change. Old surface features disappear permanently under new volcanic deposits. The previous landscape becomes completely inaccessible, buried beneath meters of fresh material. This creates a world where current geography bears no relation to past surface conditions. Underground magma chambers on O follow a dramatic cycle of collapse and reconstruction. These giant hollow spaces beneath volcanoes constantly change size and shape. When magma erupts to the surface, it empties underground storage chambers. The ground above these empty chambers loses support and collapses inward. This creates massive circular depressions called calderas. New magma gradually refills the underground chambers over time. Eventually, pressure builds up enough to cause new eruptions. The cycle repeats endlessly. Some calderas on O measure dozens of kilometers across. These enormous structures can form, disappear, and reform within decades. The constant chamber dynamics mean O's largest surface features exist in perpetual flux. Asteroids and comets hit O regularly, just like every other world in our solar system. The difference is what happens to the craters afterward. Fresh impact craters form when space rocks smash into O's surface. These collisions create the same circular scars seen on other moons and planets. Volcanic activity buries the craters almost immediately. New lava flows fill the circular depressions and cover surrounding crater walls. Within years or decades, the impact sites disappear completely. This rapid burial explains why Io shows almost no impact craters despite constant bombardment from space. The craters form but don't survive long enough to accumulate. Other worlds preserve impact craters for billions of years as permanent records of cosmic collisions. Massive areas of O's surface consist of smooth, flat plains covered in colorful sulfur compounds. These plains create some of the most visually striking landscapes in our solar system. Widespread volcanic activity deposits sulfur over enormous areas. The material spreads out as thin sheets that gradually build up smooth, level surfaces. Different sulfur compounds create different colored regions. Yellow areas contain pure sulfur. Orange and red zones show sulfur mixed with other chemicals. White patches indicate sulfur dioxide deposits. These colored plains can stretch for hundreds of kilometers without major topographic features. They create O's distinctive patchwork appearance visible from space. The smooth plains constantly receive new deposits that gradually change their colors and patterns. Io packs more different types of geological features into one small world than anywhere else in our solar system. The volcanic activity creates an astonishing variety of terrain types. Towering volcanic mountains rise kilometers above surrounding plains. Vast lava lakes create temporary seas of molten material. Deep calderas form circular canyons where underground chambers collapsed. Active volcanic vents blast material skyward while dormant cones preserve the shapes of past eruptions. Lava tubes create underground tunnels where molten material once flowed. The terrain types change rapidly as new volcanic activity modifies existing features. A smooth plain can become a mountainous region within years. This diversity makes Io a natural laboratory for understanding different types of volcanic processes. As surface experiences the most extreme temperature differences found on any solid world, active volcanic regions and quiet areas exist in completely different thermal environments. Active volcanic areas reach temperatures over 1000 degrees Celsius. Molten lava and hot gas create furnace-like conditions that would instantly melt most materials. Inactive regions away from volcanic activity drop to -180 degrees Celsius. These frigid areas stay colder than liquid nitrogen on Earth. The temperature difference between hot and cold regions exceeds 1000 degrees. This creates more extreme thermal contrasts than anywhere else in our solar system. These temperature extremes exist just kilometers apart, creating a world of fire and ice existing side by side. Volcanic eruptions don't just change local areas. They transport materials across O's entire surface through atmospheric and gravitational processes. Powerful eruptions blast sulfur particles hundreds of kilometers into space. O's weak gravity and thin atmosphere allow materials to travel vast distances before falling back down. Atmospheric winds, though weak, can carry fine volcanic particles around the entire moon. This creates global distribution of materials from localized eruption sources. Gravitational effects from Jupiter influence how ejected materials move and where they eventually land. Some particles escape Io entirely while others redistribute across distant surface regions. This global transport system constantly redistributes materials across O's surface. Io operates like a planetary recycling system where old surface materials get completely reprocessed into new geological features. Nothing stays permanent. New volcanic eruptions don't just cover old surfaces. The heat melts and chemically alters existing materials. Previous rock and sulfur deposits become ingredients for new volcanic products. This recycling process operates continuously across the entire moon. Old materials disappear, while new ones take their place in an endless cycle. The recycling happens so thoroughly that no original surface materials from O's formation remain accessible. Everything visible today formed through recent volcanic processing. This creates a world where current surface chemistry reflects ongoing volcanic activity rather than ancient planetary formation. Spacecraft monitoring have directly observed major surface changes happening in real time. This represents the first time humans have witnessed active planetary surface evolution. Voyager spacecraft in 1979 photographed specific volcanic features and surface patterns. When Galileo returned to Jupiter in the 1990s, many of these features had changed dramatically or disappeared entirely. New volcanic mountains had formed while others had been buried. Lava flows had altered entire regions. Surface colors had shifted as new chemical deposits accumulated. Ground-based telescopes continue tracking those surface changes from Earth. Major eruptions create visible modifications to surface brightness and color that astronomers can detect. These real-time observations prove that O's surface changes faster than any other world humans have studied. Jupiter's magnetic field traps something extraordinary around O's orbit. A giant donut-shaped cloud of electrified particles circles the entire planet. This invisible cloud consists of ions, atoms that have lost electrons and become electrically charged. The ions come directly from O's volcanic eruptions and surface materials. Sulfur and oxygen atoms from O get stripped of their electrons by Jupiter's intense radiation. Once charged, these particles follow the planet's magnetic field lines like cars on invisible highways. The result is a massive torus, a donut shape of electrified material surrounding Jupiter at O's orbital distance. This structure contains a vast amount of material. The plasma torus represents one of the most concentrated collections of charged particles in our solar system. Magnetic field lines create invisible connections between O and Jupiter's atmosphere. These connections work like electrical wires stretching across hundreds of thousands of kilometers. Jupiter's magnetic field doesn't just surround the planet randomly. The field lines have specific directions and paths. Some of these invisible lines pass directly through O as the Moon orbits. When O intersects these magnetic field lines, it creates a direct electrical connection to Jupiter's upper atmosphere. Charged particles can flow along these lines like electricity through a wire. This connection operates continuously as O moves through Jupiter's magnetic field. The Moon essentially becomes wired to the planet through invisible magnetic highways. Very few moons in our solar system have such a direct magnetic connection to their parent planet. Bright spots of light appear in Jupiter's atmosphere directly connected to O's position. These lights mark where O's electrical connection hits Jupiter's upper air layers. The lights are aurora, the same type of phenomenon that creates northern lights on Earth. Charged particles from O slam into Jupiter's atmosphere at tremendous speeds. When fast-moving ions collide with atmospheric gases, they cause those gases to glow. Different gases produce different colors. The result is brilliant spots and trails of light near Jupiter's poles. These O-connected aurora are some of the brightest features in Jupiter's atmosphere. They're easily visible to spacecraft cameras and sometimes detectable from Earth-based telescopes. The aurora brightness changes as O's volcanic activity increases or decreases the supply of charged particles. Electric current flows between O and Jupiter with the power of 1,000,000 amperes. This current is extraordinarily strong by natural planetary standards. The current follows Jupiter's magnetic field lines like electricity through invisible wires. Ions flow from O toward Jupiter while electrons move in the opposite direction. This electrical circuit operates continuously as long as O supplies charged particles and Jupiter maintains its magnetic field. The current strength varies with O's volcanic activity levels. The O-Jupiter electrical connection carries more current than any other well-known natural moon-planet electrical system in our solar system. Lightning bolts on Earth typically carry only thousands of amperes for brief moments. This permanent electrical river demonstrates how magnetic fields can create massive electrical circuits across space. O acts like a cosmic factory supplying raw materials to Jupiter's entire magnetic system. The Moon's volcanic activity feeds the planet's magnetic environment continuously. Every volcanic eruption adds sulfur and oxygen to the space around Jupiter. This material becomes ionized and joins the existing plasma populations in Jupiter's magnetic field. The supply process operates around the clock. Even when major eruptions aren't visible, O's surface continuously releases atoms through sublimation and smaller volcanic events. Without O's constant material supply, Jupiter's magnetic environment would look completely different. The plasma torus would gradually disperse, and the electrical connections would weaken. This makes O essential to maintaining Jupiter's complex magnetic system in its current state. Jupiter's magnetic field accelerates particles from O to tremendous speeds. Some ions reach extremely high energies. The acceleration happens through electromagnetic forces operating across vast distances. Particles get caught in magnetic field patterns that act like cosmic accelerators. These accelerated particles carry enormous amounts of energy. When they eventually collide with other materials, they can cause significant physical and chemical changes. The acceleration process creates some of the highest energy particles naturally occurring in our solar system. Some of these particles reach energies comparable to those produced by human-made particle accelerators. The magnetic acceleration demonstrates how planetary magnetic fields can create extreme physical conditions in space. O and Jupiter maintain an electrical voltage difference of hundreds of thousands of volts. This voltage drives the electrical current flowing between Moon and planet. The voltage difference arises because O moves through Jupiter's magnetic field like a conductor moving through electromagnetic fields. This motion generates electrical potential energy. The potential difference varies as I's distance from Jupiter changes during its elliptical orbit. Closer approaches create higher voltages, while farther distances reduce the electrical potential. This voltage represents one of the largest natural electrical potential differences in our solar system. It's comparable to voltages used in major electrical transmission systems on Earth. The electrical potential demonstrates how orbital motion through magnetic fields can create massive electromagnetic effects. High-speed particles constantly bombard O's surface and blast atoms directly into space. This process is called sputtering. Energetic ions accelerated by Jupiter's magnetic field slam into O's surface materials. These collisions have enough energy to knock sulfur and oxygen atoms loose from the surface. The ejected atoms fly away from O at high speeds. Some escape the Moon's weak gravity entirely and join Jupiter's magnetic environment as new charged particles. Sputtering happens continuously across O's entire surface. The process operates like cosmic sandblasting that gradually erodes surface materials. This erosion process contributes significantly to the material supply that maintains Jupiter's plasma environment. Surface atoms from O regularly escape the Moon's gravity and join Jupiter's magnetic system. This escape process operates through several different mechanisms. Volcanic eruptions blast material directly into space with enough speed to escape O's gravitational pull. Sputtering by high-energy particles knocks atoms loose from the surface. Once atoms reach space around O, they become ionized by radiation and magnetic effects. The charged atoms then follow Jupiter's magnetic field lines away from the Moon. As weak gravity cannot hold on to these energetic particles once they become electrically charged, the electromagnetic forces become stronger than gravitational attraction. This escape process continuously removes material from O and redistributes it throughout Jupiter's magnetic environment. The electrical activity around O creates one of the most dangerous radiation environments in our solar system. Spacecraft must be heavily shielded to survive in this region. High-energy particles trapped in Jupiter's magnetic field create intense radiation belts. O orbits directly through these radiation zones where particle energies reach extreme levels. The radiation consists of fast-moving protons, electrons, and heavy ions that can damage both biological tissue and electronic equipment. Exposure levels far exceed anything found in Earth's radiation belts. The particle interactions around O intensify the radiation environment beyond what Jupiter's magnetic field creates alone. The Moon's material supply and electrical connections amplify the radiation hazards. This makes O's orbital zone one of the most hostile environments for robotic spacecraft in our solar system. O does have an atmosphere, but you couldn't breathe it. This thin layer of gas comes entirely from volcanic eruptions blasting sulfur dioxide into space. Sulfur dioxide forms when sulfur combines with oxygen during volcanic processes. On Earth, this gas exists in small amounts as pollution. On O, it makes up the entire atmosphere. The atmospheric pressure measures incredibly low, thousands of times thinner than Earth's air. You'd need a spacesuit just to survive the lack of pressure, even ignoring the poisonous gas composition. This atmosphere doesn't from ancient planetary formation like Earth's air. Every molecule originated from recent volcanic activity. When eruptions increase, the atmosphere thickens. When activity decreases, it becomes even thinner. O's atmosphere represents the only known world where volcanic gases create the entire atmospheric system. Solid materials on our surface can transform directly into atmospheric gases without melting first. This process bypasses the liquid phase entirely. Sublimation happens when frozen sulfur compounds absorb enough energy to change from solid crystals straight into gas vapor. The low atmospheric pressure on O makes this transformation easier than on other worlds. Surface heating from sunlight and nearby volcanic activity drives the sublimation process. Different areas sublime at different rates, depending on temperature and material composition. This creates a dynamic system where O's surface directly feeds its atmosphere. The ground essentially breathes out gas molecules that join the thin atmospheric layer above. The sublimation process operates continuously across O's surface, providing steady atmospheric replenishment between major eruptions. Why does O's atmosphere change thickness throughout each day? Solar heating and cooling create a breathing pattern that expands and contracts the entire atmospheric system. During O's day, sunlight heats surface materials and increases sublimation rates. More gas enters the atmosphere, making it slightly thicker and denser. As night falls, temperatures drop rapidly. Gas molecules lose energy and begin condensing back onto the surface as frost. The atmosphere becomes thinner and less dense. This daily cycle creates one of the most variable atmospheric systems in our solar system. The atmosphere literally expands during day and contracts at night. The thickness variation can change by factors of 2 or more between day and night, making O's atmosphere remarkably dynamic. Massive volcanic eruptions create columns of gas that punch through O's entire atmosphere and reach into space. These pillars temporarily dominate the atmospheric system. Large eruptions blast sulfur dioxide upward at tremendous speeds. The gas columns rise hundreds of kilometers above our surface, far exceeding the normal atmospheric height. When these columns encounter the upper atmosphere, they create turbulence and mixing that affects atmospheric composition across wide areas. The eruptions essentially stir the entire atmospheric system. The volcanic columns also inject large amounts of new gas directly into the upper atmosphere. This can temporarily increase atmospheric density in regions far from the eruption source. These dramatic columns represent some of the most powerful atmospheric disturbances in our solar system. Something extraordinary happens when O passes behind Jupiter and enters the planet's shadow. Most of the atmosphere freezes out and falls to the surface. During eclipse, O receives no sunlight for several hours. Surface temperatures plummet rapidly in the absence of solar heating. Without heat input, sublimation stops completely. Atmospheric gas molecules lose energy and begin condensing onto the surface as solid deposits. Within hours, most of O's atmosphere disappears as the gas freezes out. The atmospheric pressure drops to nearly zero during these eclipse periods. When O emerges from Jupiter's shadow, sunlight gradually heats the surface again and sublimates the frozen deposits back into gas, rebuilding the atmosphere. As atmosphere doesn't spread evenly across the surface, gas concentrations vary dramatically depending on local volcanic activity and surface conditions. Areas around active volcanoes maintain much higher atmospheric densities. Continuous gas emissions from volcanic vents create local thick spots in the otherwise thin atmosphere. Regions far from volcanic activity have almost no atmospheric gas at all. These areas rely entirely on sublimation from surface deposits for any atmospheric presence. Temperature differences across O's surface also affect gas distribution. Warmer areas support higher atmospheric densities, while cold regions maintain virtually no atmosphere. This creates a patchy atmospheric system where some regions have measurable gas layers while others exist in near-vacuum conditions. Surface temperature changes directly control how thick or thin O's atmosphere becomes at any location. Temperature acts like a master switch for atmospheric activity. Warmer surface areas drive more sublimation, creating thicker local atmosphere. Cooler regions experience less sublimation and maintain thinner atmospheric layers. The relationship between temperature and atmospheric density operates immediately. Temperature changes translate into atmospheric changes within hours or days. Volcanic heating creates hotspots that generate local atmospheric thick spots. These warm areas can maintain atmospheric densities many times higher than cooler regions. This temperature control makes O's atmosphere extremely responsive to surface heating changes, creating rapid atmospheric variations. Despite its extreme thinness, O's atmosphere does generate detectable wind patterns. These gentle air movements transport sulfur particles and gas molecules across the surface. Temperature differences between warm volcanic regions and cool inactive areas create pressure gradients. These pressure differences drive weak atmospheric circulation patterns. The winds move at very low speeds due to the thin atmospheric density. However, they can transport fine sulfur dust particles over considerable distances. Wind patterns change as volcanic activity shifts and creates new temperature distributions across O's surface. Active volcanic regions become sources of atmosphericulation. These winds help redistribute volcanic materials across O's surface, contributing to the Moon's complex surface chemistry patterns. Radiation from Jupiter's magnetic environment strips electrons from atmospheric gas molecules, creating electrically charged particles. This process is called ionization. High-energy particles trapped in Jupiter's radiation belts constantly bombard O's thin atmosphere. These collisions have enough energy to remove electrons from gas molecules. Once ionized, the charged atmospheric particles begin following Jupiter's magnetic field lines instead of normal atmospheric behavior. They become part of the electromagnetic system surrounding Jupiter. The ionization process continuously removes material from O's atmosphere and adds it to Jupiter's plasma environment. This creates a direct connection between atmospheric and magnetic processes. This makes O's atmosphere a source region for charged particles that eventually populate Jupiter's entire magnetic system. O continuously loses atmospheric gas to space through several escape mechanisms. The Moon's weak gravity cannot retain all the gas produced by volcanic activity. Jupiter's tidal forces and magnetic field effects help atmospheric particles gain enough energy to escape Earth's gravitational pull. Once escaped, these particles join Jupiter's magnetic environment. The escape rate varies with volcanic activity levels and Jupiter's magnetic field strength. More volcanic activity increases the escape rate by providing more atmospheric material. Some escaped atmospheric material eventually falls back onto O's surface. However, much of it becomes permanently incorporated into Jupiter's magnetic system. This continuous escape process means Earth's atmosphere exists in constant balance between volcanic production and space loss, creating a dynamic system unlike any other world. 3 moons around Jupiter move in perfect mathematical harmony. Europa and Ganymede follow timing so precise it seems impossible. This timing relationship is called the Laplace resonance. For every 4 times O orbits Jupiter, Europa completes exactly 2 orbits. Ganymede finishes exactly 1 orbit during this same period. The mathematical ratio stays at 4 to 2 to 1 and has remained constant for billions of years. This precision can seem greater than the accuracy of most human-made clocks. Pierre-Simon Laplace discovered this relationship in the 1700s while studying Jupiter's moon system. The mathematical harmony impressed him so much that astronomers named it after him. This represents one of the most stable 3-body resonances known in our solar system. All 3 moons are slowly spiraling away from Jupiter. This gradual movement has continued for billions of years while maintaining their precise timing relationship. Tidal friction between the moons and Jupiter removes energy from their orbital motion. As orbits lose energy, they should shrink toward the planet. Instead, the complex 3-moon interaction reverses this effect. The resonance relationship forces all 3 orbits to expand outward together. As one moon moves farther from Jupiter, the gravitational connections pull the others outward as well. The outward movement happens incredibly slowly, only centimeters per year. Human civilization has existed for such a short time that this movement is essentially undetectable. This synchronized orbital evolution ensures the resonance relationship persists despite constant energy loss. Europa and Ganymede exert small but crucial gravitational effects on O's orbit. These tiny pulls accumulate over time to create significant changes in O's orbital shape. Gravitational perturbations work like gentle nudges that gradually modify orbital paths. When Europa and Ganymede align with O, their combined gravity tugs O slightly off course. These small course corrections prevent O's orbit from becoming perfectly circular. The perturbations maintain just enough orbital eccentricity to generate tidal heating. Without these gravitational nudges from its companion moons, O's orbit would gradually round out. The tidal heating would stop and the volcanic activity would cease. The gravitational perturbations demonstrate how multiple moons can cooperate to maintain extreme geological conditions. Orbital energy from the moon system gets converted into heat inside O through a complex energy transfer process. This conversion powers all of O's volcanic activity. The transfer begins with orbital motion energy. Gravitational interactions between the moons slightly change orbital velocities and positions over time. These orbital changes create tidal flexing inside O as the moon's shape adjusts to varying gravitational forces. The flexing generates heat through internal friction. Eventually, orbital energy becomes thermal energy inside O's interior. This heat drives the volcanic processes that reshape the moon's surface continuously. The energy transfer system operates like a cosmic machine that converts gravitational motion into geological activity. How did 3 moons end up in such perfect mathematical timing? They were not born this way. They were captured into resonance during the early solar system. Initially, the three moons had random orbital periods with no special mathematical relationships. Gravitational interactions gradually modified their orbital speeds over millions of years. As the moons slowly spiraled outward due to tidal forces, their orbital periods approached simple mathematical ratios. When the timing became close enough, gravitational forces locked them into resonance. Once captured, the resonance became self-maintaining. Any deviation from the perfect timing gets corrected by gravitational forces, pulling the system back into alignment. This capture process created one of the most stable multi-moon systems in our solar system. The resonance relationship has operated for billions of years and shows no signs of breaking down. This stability ensures as volcanic activity will continue for a very long time. Stability comes from the self-correcting nature of gravitational resonance. If one moon's orbit changes slightly, gravitational forces automatically adjust the other orbits to maintain the mathematical relationship. The system has survived cosmic impacts, close encounters with other objects, and billions of years of tidal evolution. These disturbances were not strong enough to break the resonance lock. Computer simulations suggest the current resonance will persist for billions more years. Barring major catastrophic events, as volcanic activity has a reliable long-term energy source. This represents one of the most durable dynamical systems known in planetary science. Each moon's mass and orbital distance contributes to the overall stability of the resonance system. Change any of these factors and the entire system could collapse. O's position as the innermost moon makes it the most important component. Its mass and proximity to Jupiter anchor the resonance relationship for all three moons. Europa's intermediate position and mass provide the crucial link between O and Ganymede. Without Europa, the outer two moons could not maintain their gravitational connection. Ganymede's large mass and distant orbit complete the system by providing gravitational stability for the inner moons. Its gravity helps maintain the precise timing relationships. This delicate balance of masses and distances creates a gravitational architecture that has remained stable for billions of years. As volcanic activity affects other moons in Jupiter's system through electromagnetic connections, the influence extends far beyond direct gravitational interactions. Volcanic eruptions supply charged particles to Jupiter's magnetic field. These particles travel along magnetic field lines and can reach other moons' orbital zones. Europa and Ganymede experience increased radiation levels due to particles originating from those volcanoes. This affects their surface chemistry and potential for harboring subsurface oceans. The electromagnetic influence operates in both directions. Changes in Jupiter's magnetic field due to solar wind variations can affect particle transport from O to other moons. This creates a complex web of indirect interactions connecting all the major moons through Jupiter's magnetic environment. The resonance system continues evolving slowly as tidal forces gradually change orbital relationships. This evolution will eventually modify O's volcanic activity levels. As all three moons spiral farther from Jupiter, tidal forces weaken gradually. Weaker tidal forces mean less internal heating and reduced volcanic activity on O. However, the changes happen so slowly that volcanic activity will continue at high levels for billions more years. The evolution timescale exceeds the remaining lifetime of our solar system. Computer models cannot predict exactly how the system will evolve over cosmic time. Small changes could lead to different evolutionary paths millions of years in the future. The gradual evolution ensures O will remain volcanically active far into the future, while slowly approaching a less dramatic state. Comparing O with Europa and Ganymede reveals what makes each moon unique within the resonance system. The differences highlight O's extreme characteristics. Europa experiences moderate tidal heating that maintains a subsurface ocean beneath an ice shell. Its volcanic activity consists of water geysers rather than sulfur eruptions. Ganymede receives minimal tidal heating and shows little current geological activity. Its surface preserves ancient features that would be quickly erased on O. Only O combines the perfect distance from Jupiter, orbital eccentricity, and internal composition to produce extreme sulfur volcanism. Small changes in any factor would create a completely different world. This comparison demonstrates how the same gravitational system can produce dramatically different geological outcomes depending on each moon's specific characteristics. During the 1990s, one spacecraft dared to fly closer to O than anyone thought possible. The Galileo mission revolutionized our understanding of volcanic worlds. Galileo arrived at Jupiter in 1995 and spent 8 years studying the planet's moon system. The spacecraft made multiple close approaches to O, some passing within a few hundred kilometers of the volcanic surface. These close encounters provided the first detailed images of active volcanic eruptions. Galileo captured volcanic plumes in action, mapped surface temperature variations, and tracked changes in volcanic activity over time. The mission's instruments detected new volcanic eruptions that had not existed during previous flybys. This proved that O's volcanic activity operates on timescales short enough for humans to observe directly. Galileo's observations established O as the most volcanically active world in our solar system and provided the foundation for all current volcanic research. Jupiter's radiation environment destroys spacecraft electronics faster than most systems can tolerate. This invisible hazard makes O exploration extraordinarily dangerous for robotic missions. High-energy particles trapped in Jupiter's magnetic field penetrate spacecraft shielding and damage computer circuits. These particles carry enough energy to disrupt electronic components permanently. The radiation levels around O exceed those in extremely intense human-made environments. Spacecraft electronics can begin failing within hours of exposure to this harsh environment. Even heavily shielded missions like Galileo could only survive limited time near O. The spacecraft's electronics gradually degraded with each close approach until some instruments stopped functioning entirely. Future O missions must solve the radiation protection challenge before attempting extended observations. Ground-based telescopes on Earth can detect major volcanic eruptions on O as they happen. This creates a unique opportunity for real-time volcano monitoring across the solar system. Large volcanic eruptions change O's brightness and color in ways visible to sensitive telescopes. Advanced instruments can detect these changes within hours of eruption onset. Infrared telescopes excel at spotting volcanic activity because hot lava and gas plumes emit characteristic infrared radiation. These heat signatures stand out against O's cold background surface. Professional observatories and even advanced amateur telescopes contribute to a volcanic monitoring. This creates a global network watching for eruption activity continuously. Real-time monitoring allows scientists to coordinate spacecraft observations with active eruptions, maximizing scientific return from expensive space missions. Landing a spacecraft on O's surface presents challenges that dwarf those faced on any other world. Active volcanism creates hazards that no current technology can reliably survive. Surface temperatures near active volcanoes exceed 1,000 degrees Celsius. These temperatures would melt most spacecraft materials within minutes of landing. Volcanic eruptions can blast debris hundreds of kilometers high with no advance warning. A landing site that seems safe could become lethal within hours. The thin atmosphere provides no protection from space radiation or meteorite impacts. Landing systems designed for worlds with substantial atmospheres would not function on O. Current technology cannot guarantee spacecraft survival for even basic surface operations in O's extreme volcanic environment. Scientists dream of analyzing Earth's volcanic materials in Earth laboratories. Sample return missions would revolutionize our understanding of sulfur volcanism and tidal heating processes. Direct chemical analysis could reveal the exact composition of Earth's interior materials. This information would test current theories about tidal heating and internal structure. Sulfur volcanic samples would provide insights into chemical processes impossible to study on Earth. These materials form under conditions that not exist anywhere else in our solar system. However, sample return from Earth faces enormous technical challenges. The spacecraft would need to survive surface operations, escape Earth's gravity, and navigate Jupiter's radiation environment. No current technology can accomplish all these requirements simultaneously, making sample return a goal for advanced future missions. Future dedicated orbiters around Earth would provide unprecedented detail about volcanic processes. These specialized missions could monitor volcanic activity continuously over multiple years. An Earth orbiter would track individual volcanoes through complete eruption cycles. This would reveal how volcanic systems develop, mature, and eventually become dormant. Continuous monitoring would capture rapid changes that brief flyby missions miss completely. Scientists could study volcanic evolution in real time rather than inferring processes from snapshot observations. Orbital missions would also map Earth's internal structure using gravitational measurements. This would confirm or refute current theories about the Moon's molten interior. However, orbital missions face severe radiation exposure that would likely limit spacecraft lifetime to months rather than years. Engineers are developing robot technologies inspired by organisms that survive in Earth's most extreme environments. These biomimetic designs could enable direct exploration of Earth's volcanic regions. Some Earth organisms thrive near volcanic vents at temperatures exceeding 100 degrees Celsius. Their survival strategies inspire heat-resistant robot designs. Biomimetic probes might use materials and cooling systems modeled after extremophile organisms. These designs could function temporarily in conditions that destroy conventional spacecraft. Swarm robotics approaches could deploy multiple small probes instead of a single large spacecraft. If some probes fail in the extreme environment, others could continue operations. These nature-inspired technologies represent one of the most promising approaches for future direct exploration of Earth's volcanic surface. Multiple space agencies are planning coordinated missions to study Jupiter's system and volcanic worlds more broadly. International cooperation spreads costs while maximizing scientific returns. The European Space Agency's JICU mission will study Jupiter's moons and the wider system. NASA's Europa Clipper mission may also provide contextual observations of Earth during operations in the Jovian system. Future missions could combine American spacecraft technology with European instruments and international funding. This approach has proven successful for other major planetary exploration projects. Coordinated observations from multiple spacecraft would provide simultaneous measurements impossible with a single mission. Different spacecraft could observe Earth from multiple angles during volcanic activity. International cooperation makes ambitious Earth exploration missions more financially feasible while advancing global scientific understanding. Exploring Earth requires revolutionary advances in materials science and engineering. These innovations would benefit exploration throughout the solar system. Radiation-resistant electronics must function for months in Jupiter's harsh radiation environment. These technologies would enable missions to other high-radiation destinations. Heat-resistant materials must withstand temperatures exceeding volcanic eruption conditions while maintaining structural integrity. These materials have applications for Venus exploration and solar missions. Advanced power systems must operate reliably despite radiation damage and extreme temperature variations. These systems would improve spacecraft capabilities throughout the outer solar system. The technological innovations required for O exploration represent major advances in space technology with applications far beyond volcanic world studies. Understanding O provides crucial insights into planetary formation, tidal heating, and volcanic processes throughout the universe. These scientific benefits justify the enormous costs of extreme environment exploration. O represents the only accessible example of extreme tidal heating in action. Studying this process improves our understanding of similar systems around other stars. Sulfur volcanism on O demonstrates chemical processes that might occur on worlds throughout the galaxy. Understanding these processes expands our knowledge of planetary diversity. The tidal heating mechanism operating in the Jupiter system serves as a natural laboratory for testing gravitational ideas in planetary systems. These studies can also contribute to broader physics research. The scientific knowledge gained from O exploration provides essential context for understanding volcanic processes on Earth and potentially habitable worlds around other stars.